Yes, now is
Okay, fine. That's great. So let me resume where I was last session, so yesterday. And today will be more descriptive, less technical in a sense. And it's more about open lines, directions of research that might be, in my own opinion, a possible selection of future research. I would like to say that there are many others. You may feel free to go to other like loop quantum cosmology and other approaches with string theory. So there are many open problems yet, but these are somehow more canonical, more conservative. And in any way, this is my sharing. This is my bequeath legacy that I can give to you. So one possibility is going supersymmetric. So supersymmetric, as sure you know, is when you have for each particle in nature, like a photon or a graviton, you can have a partner. So something which is called the photino or the gravitino. So this exists theoretically, and it's very appealing from the point of view of particle physics. Unfortunately, supersymmetry has not been found yet, let's hope it is, in accelerators like LHC. So the idea here is that you have a larger theory called supergravity, which is like a generalization of general relativity with supersymmetry. And you take this supergravity, general relativity generalized in 4 dimensions with one gravitino. This is what we call n equals 1 for one gravitino, and in 4 dimensions. You start simple. You always start simple because you want to grasp how things work. You can put a Bianchi model, you can put more things, but they will become very complicated. So let's start simple. So starting simple means putting a Friedman model with fluid or with a scalar field, a cosmological constant, simple things. So the idea is that when you put a Friedman model and you integrate over the hypersurfaces, you reduced your 4-dimensional n equals 1 supergravity to one mechanical model, which has only time independence. It still has some supersymmetry and Lorentz transformation. It requires you to also use a tetrad. A tetrad is like a square root of the metric. You see in the metric you have n square for the laps, and usually a to the square for the laps for the scale factor, and here it's just the linear functions. So then you also need to make a choice, always a choice. So you are making things simple, you made a choice. So you are keeping with that choice, and you choose a particular form. Sorry, for the gravitino. So the gravitino has this specific form. Where does this come from? Is a choice that seems to work when you go to pick up a Friedman model in supergravity with the gravitino. So it is an hypothesis. It seems to work. So in the end, you get a mini superspace with this peculiar n equals 4 local supersymmetry. Let me just tell you that you could also start not bottom up, but top down, in the sense that you pick up n equals 2 supersymmetric quantum mechanics. There are many good books on this. And people may wish to also to consider, and you then construct things. But there is no yet, to my knowledge, a description that demonstrates that what you build in supersymmetric quantum mechanics in n equals 2 supersymmetry, it's included smoothly in what you get from n equals 1 supergravity in 4 dimensions, getting this n equals 4 supersymmetry. I know my language is very dense. I know this might sound very strange and it takes time to understand these things, but I'm just putting here in front of you an open problem, something that will be interesting to consider. But why is this so? Why is this so complicated? Why look into this? Next slide, please.
Yes.
Okay, so the reason for that is that now you get a much larger Hamiltonian. Your Hamiltonian in a Friedman model in general relativity is just that first term on the right-hand side. You only have the lapse function and the Hamiltonian constraint. Now you have something that you call a supersymmetry constraint, another supersymmetry constraint where the bar over the S means complex conjugate in language of spinors, and you also have the Lorentz constraints and another Lorentz constraint. So you have more Lagrange multipliers, you have more constraints, and importantly, this is the thing. Can I ask you, Giovanni, just to press to the next item? Keep the slide, but the next item in the slide. Yes, precisely. Let it be there. So the important thing here is that when you consider the equivalent of the Poisson bracket of two supersymmetry transformations or constraints, you get the Hamiltonian constraint written in terms of spin notation. Please bear with me. I know this is strange language. This is just definition, mathematical concepts, but this is what you get for your Hamiltonian. So your Hamiltonian now is something that you obtain from a conjugation, a computation of two supersymmetry constraints. So it's like you have a square root of your Hamiltonian. So let's look at this second line here in these four equations that you see in the middle. You have that the Hamiltonian for your general relativity in your Friedman model is the typical kinetic term for the scale factor and the term of curvature. Now look, please, into the supersymmetry constraint. The supersymmetry constraints S of A and S bar of A prime, this is just notation, please. I can explain this later, but this is just notation, are linear in momentum. So the Hamiltonian is quadratic, like it should be for the kinetic energy, and the supersymmetry constraints are linear in momentum. So it's precisely almost like the relation between the Klein-Gordon equation and the Dirac equation. In the Klein-Gordon, you have quadratic kinetic terms. In the Dirac equation, you only have first-order derivatives. Right? So what now you have is that if you manage to solve this Lorentz constraint and you solve each of the supersymmetry constraints which are first order, you get a different route to solve your Hamiltonian constraint, or let's say the Wheeler-DeWitt equation. You don't need to solve the Wheeler-DeWitt equation. You only need to solve this equivalent to what could be the Dirac sort of equation, because they come from two supersymmetry constraints. The price to pay is that now you don't have one Klein-Gordon equation, but you have two sort of Dirac equations that you need to solve. So supersymmetry in quantum cosmology brings you something very interesting. Let me just say another. If you go to the famous book by Ryan and Shapley, the one that is homogeneous cosmologies, you will find in the later chapters something about quantum cosmology. They have there something that they are trying to do a square root without any supergravity. The book is from the early 70s. Please bear in your mind that supersymmetry was only created in the late 70s. It comes afterwards. So people like Ryan and Shapley did not knew what they were obtaining. They were obtaining something that was about to be displayed as supersymmetry. So this is very interesting. Then there were interesting works by Teitelbaum or Brumsat, I don't know how you call them, about all this algebra. So this is, so next slide, please. So now you do something that you can do. There are, again, there are many approaches. There are people in Mexico that treat this as the fermionic momentum as matrices. I take the sort of a Dirac, the Cambridge approach. We take the canonical momentum as derivative. So you take the canonical momentum of the scale factor as a derivative on the scale factor, and you can find a way, please trust me, where one of the gravitinos is the canonical conjugate of the other gravitino, and it can be represented as a fermionic derivative using Grassmann variables. This is a new thing about mathematics. You need to learn about Grassmannian variables that anti-commute. So this is a lot of mathematics, I know, but now I'm just trying to put to you how this is so appealing. So bear with me, please. So next item, please, in this slide. Oh, okay, so now you see, you have two operators, two supersymmetry constraints that are linear in the momentum, in the bosonic momentum as well as in the fermionic momentum. Only one derivative, d by dA, in either of them, and in another you have d by d psi dA. So they are always linear in the bosonic sector or the bosonic and the fermionic sector. So you don't have a quadratic complicated thing like the Klein-Gordon equation where you need to put boundary conditions. Here you can solve them as they are. So now, next item. The next item is just the Lorentz constraint. This is a simple thing. As you can see, the Lorentz constraints only have Grassmann variables. So now let's proceed to the next slide. The next slide, we make an ansatz. So again, you may say quantum cosmology is all about making choices and you make proposals. Yes, it is. You make proposals to see if they work. So this form that it is here for the wave function of the Friedmann model in supersymmetry satisfies the Lorentz constraint that where the Friedmann model only has geometry. You may put a fluid into that. Perfect. Now, next item. So now you see, and press again, please. Okay, let it be there. So now you see, if you use the supersymmetry constraints, which are these linear, first order linear in momentum equations on the wave function that you have just written, you get two equations. You get these equations on the B coefficient, and you get another equation decoupled on the A coefficient. They are trivially to solve. You get that for them, A and B are sort of the Euclidean exponential of A square, which is sort of the Arnold-Hawking solution if you assume that B is equals to 0, boundary condition. So supersymmetry quantum cosmology sort of allows you a different route with a lot of complicated ingredients, mathematics, which is not one that one is used to solve things that you only can take the path integral to solve it and make complicated assumptions. So this is the importance of supersymmetry quantum cosmology. However, the point is that if you go beyond this simple model, if you put a Friedmann model with a scalar field, or if you put a Bianchi model, things get very messy. It's a lot of open problems, even with the cosmological constant, and there are no known solutions. I will come to that in a moment. So supersymmetric quantum cosmology is something that was very exciting to work. I worked into that 30 or 40 years ago, and because of the complications, just got a little bit out of interest. Maybe because it involves a lot of computations. You should work now with this Cadabra, which is a sort of a new language to use to compute metrics, to compute the curvature. So it is something that it is stopped in time. So maybe young people would like to pick up as it is. It is an open issue. So now, next slide, another open ground to work with. fractional quantum cosmology. So fractional quantum cosmology is not supersymmetry, but is not less easier. This is something where the part of quantum come from the following. You can consider the Feynman path integral. I'm sure you have studied where you have these Brownian steps, where you can get the Schrodinger equation. If you consider the fractional version, which is a sort of fractal, you consider other paths. It's not Brownian paths, it's not the Feynman path integral, you have this fractional version. So the important thing here is that when you go fractional, and again, this is a lot of mathematics that I do not, it's not my beach, so to speak, but there are many books about this, you get non-local. So this means that your equations get a lot of derivatives and the same time as integrals. So this is interesting in itself. Next item. You can read this about in one of the books. So the idea, where this fractional come from? Well, this is very old. It's from the time of Leibniz. So some person, they asked Leibniz, hey, Leibniz, Gottfried, I think he's Gottfried Leibniz, I think his name. Hey, Gottfried, what can we do if n on the derivatives is not an integer, 1, 2, 3, but is a fraction? And then Leibniz replied, well, useful consequences will be drawn. Well, it seems so. So Abel, which was a famous mathematician, Liouville, even young Bernard Riemann, they came up with techniques to define and to work with derivatives of fractional order. So this means different things where n can be now not an integer, but a fraction, a real, or even a complex. So this is really an immense mathematical domain. You may say this has no interest whatsoever to physics. You would be wrong. You use this in biology to make this sort of non-local information, in electrochemistry, in other engineering, even in physics with condensed matter and engineering for materials. So a lot of things come from this. So next slide. So you can read about this in some of the papers I mentioned in one of the books. And there is a guy, I think it's in the North Catholic in Chile, called Glenny Leon, and all his, they are doing something on classical relativity with fractional derivatives. So
Yes. Yes.
there are not many people doing this in quantum cosmology.
Yes.
So the idea here is that.
Okay. I'm sorry. He's working on dynamical systems with fractional derivatives.
Okay, brilliant. No, that's good. So the idea here is, in the end of the day, you have a parameter, you have something where you have no fractional and full fractional. So it's called the Levy index. This is a mathematical definition. You can read on a review. I think it's there. And this alpha, which is called Levi or Levy index, goes from 0 to 2. And when you have alpha equals to 2, you recover your textbook quantum mechanics that you learn in high school. Otherwise, you also use fractional derivatives of order alpha, meaning 1/2, 1.3, 0.5, 1/2, so to speak. So you can do this, and you do this using these techniques that were drawn and developed by Riemann and many others. So you have different derivatives for the spatial, for the time derivative. They are called Ries and Caputo, but let's go to the next slide. So the Hamiltonian now, so I'm putting things very compact. There are quite some papers about this. So I'm just sharing with you in a compact way some things that may or may not be of your interest to read about it. So the Hamiltonian now becomes, classically speaking, a linear momentum to the power of alpha, where d alpha is not a derivative, it's just a coefficient. So alpha, you can sort of use it from 1 to 2 just to simplify things. When alpha is equals to 2, this is the momentum square, and you get a second order derivative. So this is the usual Hamiltonian thing that you know from quantum mechanics. But alpha can be from 1 to 2. So now your fractional Schrödinger equation is just the usual notation. The time you use now is just time as usual. So you are taking the usual Schrödinger equation. So then in your Hamiltonian, in your spatial kinetic part where you have the derivatives on the momentum, now you use this fractional quantum Riesz derivative. So the derivative is defined as this. You see that when alpha is equals to 2, 2 over 2 becomes 1, and you only have there the Laplacian. Very simple. When alpha is not 2, you get things much more complicated. So this is a mathematical definition. Where does this come from? This comes from Riemann and Liouville. They define it as such. It's on the books. You can also have time with a fractional derivative. It's called the Caputo derivative. Not many works have been done in fractional quantum mechanics with the Caputo derivative, but there has been. So this is next item. Please just skip the slide. Next item. Yes. Precisely. So you can do things either in the space or in the time. So this is a way to say that as far as fractional quantum cosmology goes, you are not fully relativistic. You are on a Schrödinger equation. You must go to the Wheeler-DeWitt equation, and you just play with definitions to see what comes from. So it is not strongly based. It's just a game. So next slide. Okay, so now you can take, as we did, closed Friedman with a fluid. So in this case, you can pick up the time-independent Schrödinger equation, because in your case, you are only taking the fractional derivative in space, which is the second equation, the second expression that you have here. And you see that now you have d by d alpha instead of d2 in the first line, the equation that you have there. The first equation is just your Friedman case using a Schrödinger equation with a fluid of matter, which is the time-independent Schrödinger equation. You can put it like this. Now you must go to the fractional version. So you get things that are different, and after a lot of computations and calculations, now you have things that you can balance, you can play, you can explore for different density parameters if you have different values of the fractional parameter. So you put fractional things, and you can have more or less about matter and curvature. Next item, please. The same slide, but the next item. So the important thing here, at least in my own point of view, is that you don't perhaps got a lot of interesting things in cosmology, but if you go to black holes and you try to do some quantum mechanics of black holes, and you use a fractional point of view, you get precisely the sort of holography, this projection on the boundary of the black hole, namely the event horizon, which Barrow and Salish developed. So it is quite fascinating. Barrow and Salish propose a different sort of definition of entropy for the black hole in order to accommodate holography, which is something that has come to work and to study the degrees of Friedman that define the entropy of black holes on the event horizon, but it is also possible to obtain them using fractional derivatives. So this is sort of strange. It might be useful or not for the de Sitter model. I have no idea. It's very complicated. So now another line of approach that is open ground. Next slide, please. So
Professor,
today is descriptive.
Professor, sorry.
Yeah.
What is M in that equation?
The second or the first?
The first. It can be the first. What is oh, yes,
So the first is just the kinetic term on the Schrodinger.
okay.
Then you have a potential, which is sort of like an harmonic oscillator, where you get the curvature term. The omega k is just the term for the curvature. And then you can have omega gamma and omega d that is like a fluid of radiation and dust. So this is what you get when you rewrite things in a way. This dr is actually an error of mine, is fluid dark matter. So dr here is my mistake in typing. It should be dark, dark. So the first equation is just a Schrodinger equation that you get for a Wheeler-DeWitt thing that has a fluid of dark matter. Of course, you can put the radiation or not if you wish. The second equation is what you get when you change things in order to have a fractional derivative. It just comes as that. So it is not linear. You need to change it like that. So then you solve it in terms of eigenvalues, and your eigenvalues that you get there require that you have this relation for the omega, for the radiation, and for the dark matter.
Claro.
So it is.
But and it's a mass, no? It's a mass like Planck mass or no, no? Because in this case it's late time, no? It's I don't know. I'm confusing.
Say again.
What is
Say again.
what is the parameter M? Is like a mass, I
The
think.
mass is the mass. This is the M is just like the total mass of the universe. For like you have radiation, you can have the total mass of the universe.
Ah, okay.
Like a closed. You are taking here a closed Friedman.
Okay. Okay, like the mass within the universe, observable universe radius.
Yes.
Something like this. Okay.
So this is a toy model.
Okay.
Something that has possibly no relation or no realistic connection with the observable universe. Is just a closed Friedman with a fluid matter.
Okay.
But what we did is, okay, classically simple, but let's go quantum mechanically and let's put fractional derivatives.
Okay, but why?
This was a game. Okay, we played with this.
Yes, Professor, but why we can consider like a Schrodinger equation or a wave function for a late-time universe if the late-time universe is macroscopic, no microscopic, and then how is the idea not to consider quantum mechanical description for the late-time universe?
You are right, but again, the idea is we don't care.
Okay.
So we just want to see what comes if we change a second order spatial derivative, the kinetic term, in something that is fractional. So that was our aim. So let's do an exercise. Instead of the second order derivative, let's just think okay, now I didn't understand which is the non-local effect. Okay, in order to reply to Orestes, let's go back to the previous slide, please.
Okay.
Okay, you see here the way that the Riesz derivative is defined is an integral that is all over the momentum space. So when you do this sort of differential integral expression, you are not locally making a differentiation, but you need to integrate of all values of momentum, of all values possible, at least in a range that allows you to get the momentum. So this is the non-local thing. There are more complicated aspects when you go to the Caputo. It's also a sort of a derivative that is defined in terms of an integration over time. And it's like you are derivating things locally, but then you will need an integral of your system over time. So this is strange, but this is how it works. If you ask me, why is this so? That's the way it is defined almost a century or so ago by these people, Riemann and others, in order to have these fractional derivatives. Okay, let's go.
Okay,
let's
thank
proceed.
you very much.
No problem. You must read about this in all those possible references, and maybe Leon, I don't know, maybe he's not focused. Okay, maybe he is using some derivative. So it is a good possible suggestion. Okay, next slide, please. And another, so
Yes.
more, the next one. Fine, so now another thing that was lost in time, quantum chaos, and then quantum cosmology. Why is this fascinating? Well, now a story, a sort of a personal story. In 1998, I was still making my life in United Kingdom, in Cambridge, and I attended a seminar, a talk by Neil Cornish about the work he did with Paul Shellert, which was a student of Stephen Hawking, and he was also in the audience. So this paper by 1998 has barely had any development. It is very complicated. It is basically numeric. So why is this so? Because it touches about something that is very strange, quantum chaos. So a bit of history now. So when you have chaos classically, and you go back to Poincaré and all of that, it's the deterministic chaos. So this means that if you have an uncertainty of 1 millimeter to pinpoint your grain of dust, if you have chaos, chaos means an immensely strong dependence on initial conditions, and this 1 millimeter uncertainty that because you cannot, it is a grain of dust. You have your glasses and you have your ruler and you are trying to see where is the grain of dust. This 1 millimeter of uncertainty propagates exponentially. So this means that after 1 year, this 1 millimeter for the grain of dust is 1 kilometer. So it goes from 10 to the -3 to 10 to the cube. So 6 orders of magnitude. So this is chaos, deterministic chaos. You have uncertainty, uncertainty gets propagated immensely. So next item. So how do you bring classical chaos with quantum mechanics? This is a problem that has remained for centuries. It is not yet solved, and it barely touches quantum cosmology, but is something open ground in science. So Schrodinger's equation is a linear differential equation. So chaos in classical mechanics needs nonlinearity. So how do you start with something where you work in your quantum mechanics, which is linear, and then classically you have nonlinearity, deterministic chaos. So no one knows how to do this. Next item. So many years ago, Einstein, who else, he came with a question. So maybe he had nothing to do. He had already published his papers on general relativity, and he was looking for another challenge. So he made a question. How can I justify these famous Bohr-Sommerfeld quantizations, where the n, the integer, appears, and what happens if I try to quantize something that is ergodic, that covers all the space? So he published a paper in 1917, which no one paid attention until 50 years afterwards, and another guy pick up this and start to work. And then the subject of quantum chaos start to develop, but is still yet to be fully explored. As far as we know, chaos exists classically, but how come it exists quantum mechanically? Because Schrodinger's equation is linear. How come chaos emerged? So next item, please. So chaos is something that is classically, and it needs, if we believe in quantum mechanics, it needs something that is quantum mechanically to be its seed or its reason. So quantum chaos, it is something that no one knows how to define clearly, and I copied this sentence from a book. It says it's more a challenge rather than a defined problem. No one knows yet how to define what is quantum chaos and then to put this problem. Next item. So the problem is really important. Let me say. So one aspect is to study chaos is billiards. This is fascinating. Bear with me, please. You'll see how this is really fascinating in quantum cosmology. If you consider a billiard where you throw a ball of billiard towards a line, it sort of reflects with conservation like an elastic collision. If you change the boundary, it's always about the boundary. If you change the boundary, then the trajectory may reflect or not and provide something that is an integrable system or a chaotic system. So if you now go from quantum billiard balls to something that is quantum mechanical, you have what we call the Dirichlet eigenvalue problem. There is an equation called the Helmholtz equation, and it's something like, what are the modes of a membrane where you have the boundaries fixed? Now, next slide, please. So now in 1966, so this is like a novel. A mathematician, Mark Cass, made a question. Can we hear the shape of a drum? So if you hear a drum, from the noise it makes, can you say that is a circle, an ellipsis, an hexagon, a pentagon? What is your drum? The surface. So it so happened that the answer is, generally speaking, no, you cannot. But the question is that the frequencies of vibration, in fact, depend on the shape. So a wave propagating on a domain depends on the boundary. So it is not it is not a one-to-one correspondence. You can calculate the frequencies, and from those frequencies you can more or less guess the boundary. So next item, please. So imagine that where the waves are propagating is either the mini superspace or our universe, and you want to know what is the shape of the universe. Is it a closed Friedman? Is topological our universe a donut or a Klein bottle? Is our universe a trivial topological space or not? So listening to the cosmic microwave background, like some people said, listening in a broader sense, and trying to see if you can guess the shape of the universe or the class of shape of the universe topological from these vibrations is something that is interesting to consider. Now, let's go back to quantum cosmology. So what was on that paper by Cornish and Shellert in 1998, when sort of stopped there? Not many people have done more from there. So you see, this is almost 30 years ago. So this is a very difficult, mathematically speaking, as well as physics domain. So take a closed Friedman with a scalar field. So you notice then that you can define your Wheeler-DeWitt equation using these modified variables. You can do it like this, and you can have this sort of billiard. So the universe in your mini superspace starts to behave like sort of a ondulatory behavior, like it goes to a sort of a wall in mini superspace and then comes back. It's like the mix master. You know the mix master in the Bianchi 9 is something like that. So this is just for Friedman. So next slide. So when you consider your classical model, there are inflation, there are oscillations, but you also find an interesting subset of solutions. There is an infinite set that expands, collapse, bound, goes back again, goes back again. So it's really something like in the mixed math. Next item. So this is unstable. Unstable means something that can produce chaos or could produce chaos. Next item. Then comes the conjecture. So this conjecture was made by Don Page. Don Page was a postdoc with Stephen Hawking, and he said, look, you will get solutions that have a sort of a fractal set, something very strange, in your no boundary in your exploration of a Friedman model with a scalar field within the no boundary discussion. You get a sort of a perpetual bouncing that goes expanding, a collapse, expands, collapse, something that is called in dynamical system. I'm not an expert in this. It's called a strange repeller or attractor, and you need tools like a fractal structure, which I'm ignorant about, but it's explained or sort of introduced in this paper, and something called topological entropy. Do not ask me what it is. I don't know. This is what was in this paper. So next item, please. So the no boundary solution, which is something where this was analyzed, it sort of brings chaotic behavior in some subset. So it sounds that the WKB is breaking and the no boundary could be losing some appeal. Next item. So this is open. To my knowledge, no one had tried to study chaotic behavior like they have done within the no boundary, within the Vilenkin proposal. Because the Vilenkin is also WKB and depends a lot on the outgoing. Can you have quantum chaos there? I have no idea. So this is again an open domain, generally speaking in science, quantum chaos, and also an open, untouched, barely touched domain, barely explored, that people have gone to. It's like in the old days when people went down south along Chilean coasts and they went to see the Magellan Strait and then Antarctica and all that, and you cannot explore this strong storm, so it's terrible. So the maps, you don't have a satellite, so it's still to be explored. Next slide, please. Just bring it. So now, continuing with quantum cosmology. So this is a quote by Hermann Weyl about what was happening many years ago in mathematics. So he says that at that time in mathematics, people were either studying topology, which was nice, and shapes, or something very hard to understand, what was abstract algebra. So he said that topology was driven by angels and algebra was driven or ruled by demons. So they were trying to get our souls for it. How does this relate with quantum cosmology? So please do not forget that, namely in the no boundary case, the Hartle-Hawking is a little bit about topology, about what you choose for your geometry that dominates the path integral. And when you go to supersymmetry, you are using a sort of an algebraic way of solving your system. So the idea here is, let's try if we can relate the possible sets of boundary conditions with the constraints, and if there are something hidden there. So next item, please. So now maybe it is something that I didn't explain enough, but it's the following. So you can make your quantization of your cosmological models two ways. You can do it Dirac way. Dirac way is you get the constraints, you transform the constraints in differential operators, you put the wave function in front of the differential operators, you solve it, you get the wave function, subject to that constraint. So the constraints impose that you identify the true degrees of freedom. So it's like if you have a motion on top of a table and there is a constraint, like you must be on top of the table, this constraint tells you, okay, you have 3 coordinates, generally speaking, X, Y, and Z, but because of the table, the constraint, you only have 2. So either you solve the constraint and you only use 2 of the degrees of freedom, or you solve your motion, generally speaking, under the forces that is subject to, and then impose the constraint. So in either way, you always get the proper description. So this is more or less the idea of Dirac. So now we are going to use something called the reduced phase space quantization. So it's different. What happens here is that you have all the degrees of freedom in your system, and you solve classically your constraints. If you have 10 degrees of freedom, like initially you have in your metric, because it's 4 by 4 and it is symmetric, so you have in principle 10, generally speaking, degrees of freedom. If you have some constraint, you can come up with 10 just with 2 or 3 or 4, because you have some constraint that you imposed on your system. So this phase space that you obtain may have symmetries. Those symmetries now are not the symmetries of your space-time, but they are sort of related, and they are systems that you have in your dynamical system. So your phase space also has invariant quantization, and you quantize whatever you want. So please, let me resume to make this clear. You have 2 options. Either you solve your system with the full constraints, with the full wave function, or you solve it classically. First, you reduce the degrees of freedom, and then you have another equivalent thing, which is the reduced phase space. So this means that you can have another Lie algebra for the reduced phase space, and you get a wave function of the reduced phase space. So this allows in some way to bypass the sort of boundary conditions that you need to impose previously. Next item. So this is in that book on the World Scientific that I sent to you. So this allows to bypass the having to impose proposals. You don't have to make a choice. You are just doing mathematics. You have your system, you have your equations, you have your constraints, you have your algebra. You don't worry about topology. Let's just solve it. So next item, please. So this is still 1967. This is still Bryce DeWitt. This is called the Bryce DeWitt conjecture. So he made a conjecture. He said, I don't care about boundary conditions. I only care about the constraints. I'm going to solve them, get the true degrees of freedom, and nothing else but the constraints are needed. So this is an open thing that is to be done. Not much has been explored in this case, which is how to compare what you do with full configuration of full superspace or mini superspace, or when you reduce it, solving the constraints. So this is an open direction as well. Next slide. So I'm giving you a lot of, not exhaustive, because there are many other open problems, and I will come to this in quantum cosmology. So now, challenge. Can quantum cosmology be observational? Well, can we make predictions that we can detect up there in the sky? Can we see quantum cosmology on the primordial perturbation in the cosmic microwave background? Yes or no? I don't know. But next item. So now this is a work that mainly Klaus Kiefer has done. And in a sense, he considered that we are in a semi-classical gravity or quantum field theory in curved space, where you can make curvature weak or not so weak, but you do it perturbatively in a way that you are exploring. So you are making corrections to the quantum fields. So this is sort of, you can say that that Hawking has done for the black hole and others for the sitter, but we are taking this a little further away. Next item. So you can, and this is something that is in the work that Klaus Kiefer has done with collaborators, some guys in Bilbao as well, you can modify this L, this C of L is just L, the letter. So this is, there is a missing slash there. So you modify the primordial power spectrum. You modify whatever you get for the cosmic microwave radiation when you consider quantum gravitational modifications. You can do that. So you get signatures and you can sort of try to identify them. The problem is you can compute them, you can make a scale for them, you can say the number of the magnitude, but they are still extremely small and non-detectable with current technology. So no way you can see them. If Klaus Kiefer is right, they are still up there, but it's very difficult to extract them. But this is an open ground. Perhaps this is the open line that there is a lot that has been done recently, but you may want to look at it. Next item. So there is also the problem of regularization, but this is more theoretical. So this is something that you may wish to look and consider if you are curious about this is, okay, does quantum cosmology bring me inflation? Yes. Is inflation okay? Well, I think so. Does it bring good observational quantities to select which boundary condition? And if the inflation is good enough, well, not yet. So this is something that is open. So I'm coming to the end, but let me now come and present to you more ideas. So next slide. Okay. Many ideas that you may consider or not. So picking up with the previous slide is, can you work out quantum cosmology to become observational? No one has yet done more than Klaus Kiefer. Can quantum cosmology with strings or supersymmetry also become observational? No idea. Can you also predict the Bunch-Davies and variations of the Bunch-Davies from quantum cosmology? Open problem. Next, number 3, can you pick up the algebra of constraints and impose there that you have torsion? So this means torsion in the sense of the Einstein-Cartan-Sciama-Kibble description. You have fermions explicitly. Can you do anything and extract observational consequences? No idea. Then from 4 to 7 are just items on supersymmetric quantum cosmology. How can n equals 2 supersymmetry be retrieved? I don't know. If you put matter in your supersymmetric quantum cosmology, can you work it out in a way to extract reasonable results? No idea. So there are a lot of problems. What if you put a Bianchi model with a cosmological constant? No solution yet to be found. And what about if you have corrections on the Schrödinger equation? We saw many slides before with the perturbation of the scalar field. What does that bring? I don't know. So next slide. So the next slide is a bit like a knowledge diagram. Maybe you cannot see it perfectly. This is inspired by the Ryan and Shapley book, where he has a lot of this. So the idea here is that you want to get the quantum gravity theory, and one possibility is to use something that I have not talked about, but is a sort of a deformation of quantum mechanics. It's called quantum groups. This is very mathematical, and you might consider that. Another possibility is to change the number of dimensions. So this means, again, fractional quantum mechanics. And then you may consider or not this spectral variation. So there are many directions to explore, and not much has been done. Next slide, please. The next slide is basically, again, in quantum, chaos, and supersymmetry. So you have superspace, you quantize it, and then you expand things. Now, sex expansion here is X-even expansion. I'm just expanding things on the solution of the Hamilton-Yakob equation. So you can do two things now. You can consider orthogonal corrections on your mini superspace hypersurface or tangential. If it is orthogonal, you can make some predictions changing your Schrödinger. Tangential means a lot of problem. You lose WKB, you lose non-unitarity, and you don't know how to relate this with quantum chaos. There are works by some guys that use a generalization of the Feynman path integral. It's called the trace formula. It's relating with quantum chaology by a mathematician, a physicist that's still alive among us, Michael Berry, and is the one that is saying, well, maybe in the end of the day, you will stumble on that problem that is among us from more than a century, which is the Riemann hypothesis. That's where quantum chaology is. So you see, this is many doors, many roads, and many stones where you can stop and fall over. Next slide. So now, still in quantum cosmology, when you have boundary conditions, you always have degeneracy, meaning that you don't have only one solution, you have a lot of solutions. How do you solve this? So one possibility is the Witt conjecture. You don't care about the conditions, and somehow the Witt conjecture is related with having hidden symmetries, and maybe you require here supersymmetry. Remarkably, there is this mathematical tool to compute the path integral, where it is called the Picard-Lefschetz, and the Picard-Lefschetz is related with Morse theory that Edward Witten coined some time ago, and it involves supersymmetry. So as you see, as you go along and you get to my age, you get a fascinating perspective of life, of the universe, but also you are tired, you are old, and you cannot do anything more. Next slide. So I'm finishing. So in the next slide is just what can you consider? So my humble suggestion, there are two main works for you to consider, in my humble opinion. Klaus Kiefer book, Quantum Gravity, and also this that is open on the archive by David Wiltshire. They are the things, namely Wiltshire, that are close to a textbook on quantum gravity and cosmology. You have these good other books like this by Ryan and others, but in my opinion, these ones in boldface are the ones that I should consider to learn about it. Next item, please. Foggy, you have this that I have sent to you because they are not as good, not close to what David and Klaus have been done, but you can say on the supersymmetry and more challenging stuff, look into them. If you are curious and you have attended these lectures just to learn a little bit about quantum cosmology, there is something on the sort of outreach, next item, which you can take anteprandium. Anteprandium comes from Latin and means before you take a meal. So before you go into this big meal of quantum cosmology, you have this slide in the slide share with like a talk that I give some years ago. So next slide will be the final one. So thank you very much. You have here my email and you have my LinkedIn connection where you can sort of perhaps get more details and more documents about me. And that's it. I hope you have enjoyed it. Thank you very much. My pleasure.
Thank you, Professor, for this very nice mini course. Okay? And your
Thank you.
references also, no? And then, are there any questions? from the students, professors?
No questions. Everybody is up. Thank you.
There is a question. Yeah.
Bastien
Bastian.
is clapping. Thank you, Bastien. Thank you. My pleasure.
Good, good. Professor, I have a question. Yes,
Please.
I'm very interested, no, in the connection between quantum cosmology and inflation, particularly the predictions, corrections for the predicted corrections for the power spectrum and the other inflationary observables. Then I know, no. From the yes, in inflation in sub-horizon scales, the fluctuation in the fuel are created through quantum mechanical processes, and then after the horizon crossing, these fluctuations transition from a quantum to classical behavior. Okay, and then in this case, it's possible to understand this quantum to classical transition from the point of view of a quantum cosmology approach or model?
Yes, and to my knowledge, it has been done. So I'm saying this to you because you should really look into the book by Klaus Kiefer, because when I say the book is because he has done a lot of his work in his life. He's retiring. He's also a bit, he has not been good of his health. And if you get an end on the book, I don't know if there is available a cheaper copy. I don't have it. I only have the a printed copy in the library. He worked on this in the 1990s and recently with these people in Bilbao and a student of his. And it is more or less summarized in that review I sent you on classical quantum gravity. So I will say, in my educated guess, that the answer to your questions is definitely yes, it has been done. The problem is that whatever you obtain within general relativity in some small deviations, so it's like quantum field theory in curved space where you put the curvature, not just classical curvature, but with a more increased curvature in the sense that the quantum mechanical thing is a little bit unavoidable. You need to consider perhaps other types of gravity, say scalar tensor like Brans-Dicke or strings or something. You really might have to consider that. Maybe supersymmetry, I don't know. So the question is, there are predictions, quantitative predictions, with plots, with peaks and frequencies, but they are not within the reach of our technology. So maybe you need to change, not to just to consider the quantization of general relativity, but something else. I don't know.
Okay. Okay. Thank you, Professor.
No problem. My pleasure.
Okay. Questions? Okay. I think perhaps the students could be writing to you, Professor, after the mini course. Okay. And then
Perfect. No
if they
problem.
have some questions. Okay. And then, yes, thank you very much.
Let's be in touch and either speaking or typing. And if I can be of any assistance, let's keep in touch. Okay. Maybe I will think about it if I get my retirement, and I will do this motorcycle travel from
Portugal.
where you are, Arica,
Arica.
Arenas in the deep south.
Good, very good.
Ecuador.
Yes, I hope not to
Thank
meet.
you so much.
Yes, I hope to meet you again. Okay, and then thank you very much. Okay.
Thank you so much.
Yes, okay.
Abraço. Até a próxima.
Abraço. Até a próxima.
Thank you, Professor.
Bye. Thank you.
Thank you.
No problem. My pleasure. Thank you.
Bye.
Thank you.
Okay. Yes. Then bye bye for everyone. Okay. Thank you for your participation.
Bye.
Bye bye.